All right, so let's look at paper 2, question number 11. Right, what has been told was in the cyclic quadrilateral ABCD. So ABCD, BC is equal to CD, which has been already marked. The chords AC and PD intersect at D. X is located on the tangent. So what's the tangent? This black color line is the tangent. So this black line going from X to B. So X is located on the tangent drawn to the circle at point B. All right, so let's look at the first requirement. What have they asked us? Show that angle CBX. So where is CBX? CBX. That's this green color angle. The angle that I've colored in green is equal to angle CAD. So where is angle CAD? That is the angle that has been, okay, let me color that in orange. You have been asked to prove that this green angle, the angle colored in green, is equal to the angle what I'm coloring now in orange. All right. How do we do it? Before we start writing the proof, let's take a pencil and mark the equal angles. Let's start with the green angle, the angle between the angle made by the tangent and this chord CB. Let me highlight the chord CB for you all. Let me bold it. So to make this green color angle, what are the lines that I've got together? That is the black tangent and the blue color code CB. So let me show you the blue color code CB by darkening it. All right. So let's call, or let's put X with it, X for that angle. The green angle, let's call it X. Or since X is there, I'll use some other letter, maybe Y. I'll use Y. All right. Now, if this green angle is Y, what should be this yellow angle? It too should be Y. Why is that? It's the alternate, what's the theorem I'm using? Alternate segment theorem. So what does alternate segment theorem say? If a chord is participating to make an angle with the tangent, and if the same chord subtends an angle at the circumference in the opposite segment, then they are equal. All right. So due to that reason, see this blue chord CB, it is participating with the tangent to make this green angle, and that same blue chord has dropped or has subtended an angle at the circumference. See, from C it's starting and from B it starts. So which chord has subtended this yellow color angle? Chord CB. It is the same chord who helped the tangent to make this green color angle. Therefore, these two are equal. Under which theorem? Alternate segment theorem. So we'll just remember that. How did we get to know these two? The green angle is equal to the yellow angle using the alternate segment theorem. Right. What's the next thing? The next thing what we can say is this yellow angle and this black color angle, they have been subtended by the same arc. Which arc has subtended this yellow angle here and the black angle? What is at D? Look at the arc. Which arc is it? It's arc CB. Arc CB is the one. See how the lines go. Let's draw the lines from C. This goes, and from B, here it goes. So what does that mean? This black angle has been subtended by arc CB. And look at the yellow angle, which we have marked as Y. That also has been subtended by the same arc CB. So we can apply the theorem of what? Angles in the same segment. So what should be this black angle's value? Y. So how did we find? By using the same segment theorem. Same segment theorem. All right. Now, look at this blue colored triangle. In the blue colored triangle, we have been told that CB is equal to CD. So the blue triangle is an isosceles triangle. So we know in an isosceles triangle, opposite angles are, or rather, side angles opposite to equal sides are equal. I repeat, in isosceles triangles, angles opposite to equal sides are equal. So what are the two angles opposite to equal sides? That is this one, this pink angle, and the black angle. So for the black angle, we have put as y. Then what should be the value of the pink angle? That too should be y. All right. Now check who has subtended, which arc has subtended this pink angle, what I'm coloring now. Go back and see. If you go back, you see, you get C. If you go back from the place where the angle is, if you go and see from where is it starting, you get C, and the other arm, if you go back, you get D. So this pink angle has been subtended by arc CD, the green arc. Any other angle subtended by the green arc at the circumference? I see one. What is it? The orange angle. See, if you come back and see along the arm, you get C and you get D. So orange angle also has been subtended by the green arc CD. So if an arc has subtended multiple angles at the circumference, all of them are equal. So this too should be Y. What do we call that theorem as? Angles in the same segment. All right. So now let's see what was the requirement. We have been asked to prove CBX. What is CBX? The green angle is equal to this angle CAD. CAD. That's the orange angle. See, we have Y for the green angle and we have Y for the orange angle too, which means these two are equal. Now we have to tell the story in our answer. How did we get Y and Y? Or how did we figure it out? This green angle is equal to the orange angle. We have to tell that story to our examiner. So let's start telling the story. All right, so here we go. What's the first thing we figured out? We figured out this green angle is equal to the yellow angle. So let's say that. What's the green angle's name? Angle CBX. So CBX is equal to the yellow angle. What's the yellow angle? AC, or rather, yellow angle's name is BAC. And why did we say those two are equal? What was the theorem? Alternate segment theorem. That's what we write within the brackets. All right. And what's the next thing we told? The next thing we said was the y's, or rather, the angles subtended by the same arc. We figured out this yellow angle and the black angle. Both of these are subtended by the same arc. What arc is it? It was both of them are subtended by the arc BC, this arc. Let me show you this arc BC. So let's record that. Let's say that to our examiner. What is it? Angle C, or rather BAC and BDC. So the black triangle's name is BDC. So BDC is equal to the yellow angle. What's the name? BAC. What's the theorem? Angles subtended by the same arc. Angles subtended by the same arc at the circumference are equal. What's the name of that theorem? Same segment theorem. Or angles in the same segment. We can write angles in the same segment. That's the name of the theorem. All right. What's the next thing? The next thing we said was, if this black angle is y, the pink angle too should be y. Why is that? Because they are equal angles in an isosceles triangle, or they are angles opposite to equal sides in an isosceles triangle. So let's say that we said angle BDC, that's the black angle, is equal to the pink angle. What's the pink angle? CBD. What's the reason? Angles opposite to equal sides in a triangle. All right. What's the next thing? Then we said this pink angle should be equal to the orange angle. Why? Because both of these are subtended by the green arc CD. So let's report that. What is it? CBD is equal to, the pink angle is equal to the orange angle. What's the name? CAD. What's the reason? Angles in the same segment. All right. So now, what are we supposed to prove? We are supposed to prove the green angle, that is this, CBX is equal to CAD. All right. So we have already proven it. So we can say that. Now, what can we say? We can say CBX is equal to what? BAC. See, that's what we wrote initially. And BAC is equal to what? BAC is equal to BDC, the black angle. We have written it. See, BAC equals BDC. And what is BDC equal to? BDC is equal to, look at the third line, to the pink angle, CBD. And what is CBD equal to? We have proven it is equal to CAD, the orange angle. So then what can we say? So we can say, so what can we say? Then we can say angle CBX is equal to what? Angle CAD. Why? See, look at the ends. CBX equals BAC equals BDC equals CBD equals CAD. All right. So we have proven that CBX is equal to CAD. D angle. All right, so let's look at Roman 2. What are they asking in Roman 2? Show that AB is to CD is equal to AP is to TP. All right, so when I see something like this, ratios in a geometric question, the ratio between sides, the very first thing that comes into my mind is similar triangles. Because we know if two triangles are similar, their corresponding sides are proportional. So it's highly likely the examiner is trying to test that knowledge of ours. So let's check. Look what they have said. AB. What's AB? AB is a side of this blue color triangle. And AP. What's AP? That's also a side of the blue color triangle. And what is CD? CD is a side of the green triangle. And what's DP? DP is a side of the green triangle. All right. So it's highly likely that they are trying to test our knowledge of similar triangles. So let's check whether this blue triangle and this green triangle is a pair of similar triangles or not, right? So let's take the two triangles. What is it? Triangle. What are the two triangles? What's the blue triangle's name? Triangle ABP. And what's the green triangle's name? CTP. CDP. CTP. Right. So how can we prove that two triangles are similar? One way is if we prove that blue triangle and green triangle is a pair of equiangular triangles. What are equiangular triangles? Triangles with same set of angles. Now for an example, let's say there's a triangle like this. Let's say the angles are 45, 55, and 80. And there's another triangle, and these are just sketches, okay? 45, 55, and 80. What can you say about these two triangles? They are equiangular. And when it comes to triangles, if triangles are equiangular, they are similar too. That is a rule applicable for triangles. If two triangles are equiangular, they're definitely similar too. All right. So let's say you have been given two triangles, but not with all the angles. Now, for an example, let's say you have been given a triangle. This is, let's say, 43 degrees, and this is, let's say, 87 degrees, and there's another triangle, 43 and 87. Okay, only two angles of each triangle are given. Are these two triangles equiangular? Now, what are equiangular triangles? All three angles of one triangle are equal to all three angles of the other. What does that mean? The same set of angles. But the problem is, in the first triangle, the angle is missing. The top angle is missing. In this two, all right, then are these triangles equiangular? We have 43, 43, 87, 87. So just by looking at two pairs, 43, 43, one pair, 87, 87, one pair, can we say that the triangles are equiangular? Yes, we can. Why? If two angles are equal, definitely the third one is going to be equal. How? We know in a triangle, angles add up to 180. So look at the first triangle, 43 and 87. That would give 130. So what will be the top angle? 50. And what will be the top angle of the other triangle? That too is 50. So in order to prove that two triangles are equiangular, we don't need all three angles. If you just prove two pairs of angles are equal, that's enough. All right. Okay, so bearing these facts in our mind, let's try the question that has been given to us. So we know in triangle ABP, can you see when we did Roman 1, we put y, we have put a y here and a y here. What does that mean? They are equal. So let's say that. What is it? Was that up angle, up blue triangle's y's name? BAP. So angle BAP is equal to the y of the green triangle. What's the green triangle's this y name? CDP. Angle CDP. So tell your examiner why you wrote y and y there. It was because both these angles, BAC or BAP and CDP, are subtended by the same arc, by this orange color arc. Now, when we say BAP, you won't realize it, but this one has another name. What is it? BA. Without saying P, we could have said BAC2. So BAC, and same with this down Y. When we say CDP, you will not realize the arc, but this one has another name. What is it? CDP. CDP. So both of these Y's are subtended by the same arc. That's the reason why we say they are equal. So angles in the same segment. We have already proven in Roman 1. So if you don't like to write the theorem again, you can simply say proven in Roman 1. Even that is fine. We have already said in Roman 1, these two angles are equal, right? Right. So then what is? We got one pair, we need two pairs. What about this angle? This angle where I put a tick and this angle where I put a dot. Those two angles have to be equal. Why? They are vertically opposite angles. So what's the angle with a tick? That's PTA equals, what's the angle with a dot there? CPD. Vertically opposite angles. Don't write shortened forms in the same way I'm writing. You have to write the entire word. Vertically opposite angles. All right. Okay. So now we have proven two pairs of angles are equal. Therefore, what can we say? Therefore, triangle ABP, the blue triangle, and triangle CDP are equiangular. Are, are we'll say is a pair of equiangular triangles. All right, so we said our examiner, we know these two triangles are equiangular triangles. Now we'll tell our examiner that we know if two triangles are equiangular, they're definitely similar too. Hence, you can say hence or therefore, whatever, or then, whatever you like. Then triangle ABP and triangle CDP are or is a pair of similar triangles. If two triangles are equiangular, they're definitely similar too. So similar triangles. All right. So now we have proven these two triangles are similar. The blue one and green one is a pair of similar triangles. Now, what do we know about similar triangles? What do we know? In similar triangles, corresponding sides are proportional. So let's apply that theorem now. All right, so let's tell our examiner that we know corresponding sides of similar triangles are proportional. So what does that mean? So therefore, right. So corresponding sides of similar triangles are proportional. Therefore, right. So let's try the corresponding sides ratios. AB is to, what's AB's corresponding side in the green triangle? Where is AB in the blue triangle? That's front of this, right? The tick. And while ago, we have proved that tick and the dot are equal. So for a while, we'll put a letter. If the tick is T, the dot is also T, right? So where is AB in the blue triangle? Front of angle T. And in the green triangle, what's in front of angle T? What side? That is CD. So AB and CD are the corresponding sides. So what do you write in the denominator? CD. This ratio is definitely equal to what? The ratio of other two corresponding sides. What is it? Um, they want us to take AP, so let's take AP. AP is to, what's the AP's corresponding side? Where is AP? AP is front of the empty angle where we haven't marked anything. So in the green triangle, what's in front of the angle that has been kept empty? This one. What's in front of it? That's DP. So AP is to DP. So AB is to CD is equal to AP is to CD. Did I write? It's not CD. Sorry, my bad. What's in front of empty angle? That's what's this side name? DP. Sorry, my bad. So I should write AP is to DP. What's the reason? We have already written the reason why corresponding sides of similar triangles are proportional. All right, so we have done Roman 2 completed.